Okay, well, I'm Ken Ham, President of Anderson Genesis Creation Museum in the Ark Encounter. We're back for part 2. We came here to 3D Engineering Solutions to look at their CT scanner and to show you inside our Allosaurus skull that they put in the CT scanner, and we were talking about that, and then for some reason our signal decided to cut out. So we're connected now to Wi-Fi inside the building, and so this should work really great. And here we are with Rob again, who's a job here. You're the Vice President of Operations, and we have James, who is an engineer. What sort of engineering again do you have as a background?
I'm a senior project engineer. My background's in electronics, electrical engineering. I've worked at a company called Battelle for about 20 years, and I ran their CT systems. And then I went to a company that writes the software that we analyze with, and then I came here.
So you understand a little bit about CT scanners?
Just a little bit.
Yeah, probably at least that much more than I know.
When you work on the best equipment in the world, you've got to know your stuff.
I would have no idea what to do with any of this. Anyway, we were just over there at the CT scanner, and Rob, you were telling us about the scanner here. So this is not something we'd just buy to have at home, right?
No, and not unless you have a lot of disposable income.
So this is a pretty expensive piece of equipment.
This one's $1.2 million.
$1.2 million?
Yes, it's the most advanced CT equipment that you can buy at the moment. It is made by Nikon. It's a Nikon piece of equipment.
So it comes from?
This one is particularly manufactured in Tring, England.
In England. And $1.2 million. Hey, Andrew, how much was our Allosaurus actually appraised for?
Just over $1 million.
So do you realize, see that skull over there? There's a cast of our Allosaurus. The real skull is now back at the Creation Museum, and this is a cast that we have here there for measurement purposes. But the real skull, you had the real skull here. Yes, that was a pretty delicate operation too, moving that from the Creation Museum to here.
We had to wrap it up in pieces so that it could be carefully put in the scanner with pads, because the X-rays can see through all the packaging, so that protected it, bringing it over here and setting it up in the scanner. And also the skull is so large, even though the scanner is the biggest available, we still had to tip the skull over to do it in several sections to do the full scan.
So it was quite an operation. And James, I asked you before, but I'll ask you again because it cut out before, but what's the most interesting item you've ever been involved with in doing a scan of?
This Allosaurus skull is definitely the most fun and interesting. It was also the most challenging thing I believe I've done to date.
Well, see, that's good experience, right?
Absolutely.
For the future. And as we said, you have hundreds and hundreds of customers, and not all of them have Allosaurus skulls to scan.
No. Most of them they're still very exciting things, aircraft parts, automotive parts, medical things.
So can we actually go inside a
Absolutely.
CT scanner here? Okay. So let me see if I can get in here with you.
Put your head in here.
Oh, it's not going to X-ray me while I'm in here, is it?
No. Behind you is the X-ray source, and it's a 450 kilovolt source. The X-rays will come out of the center of this in a cone beam. Your parts will sit on this turntable, and the cone beam will go through the parts and hit a detector. We have two different types of detectors on this. We have a 16 by 16 inch Perkin-Elmer detector, and then a CLDA, curved linear diode array detector behind it. Each one could be used. And what happens is, as the cone goes through the material, only a certain amount of the X-rays make it to the panel, and then that makes an X-ray image. You slowly turn the rotating table, you take thousands of those images. Now you have thousands of X-rays that you put together into a 3D voxel volume. A voxel is a volumetric pixel, and before you get that, you have to reconstruct all of those images into that volume.
Oh, that just sounds like a easy afternoon's work.
It's easy for the software, for those who know.
For those who know. Tell you what, I'll get our videographer, Maria. Do you want to jump inside there so people can actually go right inside and see what we were talking about? And
so to the left there is the source where the X-rays will come out. And you can see there's 225 kilovolts on top, 225 on bottom, and those add to 450 kilovolts. And to the right, you'll see the where the detector is, the 16 by 16 per kilometer detector, and behind it, if you even look over it, you'll see a curved linear detector that is used for getting rid of some of the noise that can be inherent in some of this work.
So let me just check with our videographer. Do we have any people asking questions, Maria? If anyone wants to ask questions, they could. Well, I have the people here who know what they're doing.
Someone said, just curious, could a 3D printer have done the same thing?
No. The work that we do here with CT scanning, laser scanning, structured light scanning is kind of precursor work to what you would do for 3D printing. So if you have an object that you want to accurately replicate, you have to have a model of that object before you can replicate it, and that's the type of work that we do.
That we do here. Okay. So let's move on over here. So that's where the Allosaurus skull actually sat on that stage there.
Correct, right. And it's cardboard barrel with foam inside of it. So we never really actually saw the skull, only the barrel.
Okay.
And you can see the size of it of the image area is smaller than our skull. So that's why we had to do one set of images and then turn it up the other way
And do
to
another,
do another set of images, and then James has to stitch it all together, which is why we use the cast. They laser scan the cast here so that they could put that image in the computer and then line up all the X-ray images around that cast to anchor it.
Now that skull is about 97% complete. It's the most complete Allosaurus skull
As far as we know,
in the world.
The biggest and the most complete.
The biggest and the most complete. And it's interesting that skull is worth about the same as what this piece of equipment here is worth, just because it is so rare. And,
well, you can order one of these and get it built for you. So they're more easily obtainable. Our Allosaurus skull isn't.
Oh, that's true. That's true. And you wouldn't use one of these in the hospitals anyway because
That would
your
kill
patients
somebody.
wouldn't survive, right?
Yeah, typical CT scanners run at somewhere around 60 to 80 kilovolts. This is a 450 kilovolt machine. That's not good for people.
That's not good for people.
That gives you better quality data.
So
Here's another question. How long did this process take?
The scanning process took, we did it over a series of a long period of time, and I don't know, the total scanning time, Jim, what would you guess that would be? How
I
many
don't have a
hours
total hours, but it took 5 scans to do each mandible, so the lower jaw bones, and I took approximately 9 to 11 scans of the skull itself.
how long does a scan average take, would you say?
On the mandibles, I think they were about an hour and a half, and on the skull, it was probably about a 2-hour scan per.
This was over about a 5-month period it was done.
20, 30 hours, somewhere in that range, maybe 20, 50 hours, somewhere in there.
That's a lot of scanning.
It is a lot of
Somewhere
time.
around there, 30 plus hours.
30 plus hours. Okay, well let's move on over here. I know you didn't see the real skull. You can if you come to the Creation Museum. You can see the real skull, but we have a cast of it here. But we have some interesting things on screen here that James is going to show us. So we're going to actually see inside the Allosaur. So we can see, let me get over here with the microphone, and so James can explain what we're seeing here.
So this is the completed full CT data set. It's incredibly huge. It takes up anywhere from 60 to 100 gigabytes of data in RAM current memory. The bottom here, these are the lower mandibles, so each one of these was done in several sections and stitched together. The top of Moore's Law.
There we go. We're back on.
Okay.
Okay, we're having a little connection issues here, so there was an overload of data. There's so much data in the computers from from the CT scans. I think we had an overload. No, anyway, James can continue.
Okay. So there were many pieces of the skull that were in different segments, and in order to put that together, we actually laser scanned the casting of the skull, and I overlaid the casting, and I could use that to locate where all the other pieces went together at. When you're done with the 3D model, you can move it around hopefully. You can see how much data this has taken up. But you can rotate it, you can flip it, you can slice through it, and do a lot of investigation with that in particular. Also, in order to get this to even fit into the computer the way it is, I had to cut the data set in half down to an 8-bit data set instead of a 16-bit data set. And I have the original 16-bit data set still intact, so if anybody wants to look at this later, they can look at it in great detail. And I'll show you some of that on the other computer.
So I remember my first computer, I thought it was really great. I had a 10 megabyte hard drive, and I thought that was great.
I remember the floppy disk you had to put in and out.
Yeah, then I ended up with 5 million floppy disks.
Kilobytes.
So this is a T-Rex egg that you also scanned, and this is a cast of the actual skull, but we had the real skull that you scanned.
That's
but
our Tyrannosaurus egg.
that's the Tyrannosaurus eggs, and we'll have a look at that in a moment. But everyone wants to know what size the brain was, and can we go inside the brain cavity, and you did that, right?
I did. What I believe is the brain cavity is shown on this monitor in pink. It's a nice brain color.
This is
So-
an image. This is an image of the space.
So what we'll do is, I'll get Maria to come over here. Could you show us, James, at the back, that front area?
Sure.
Is that hole, probably where the spinal cord comes through, right?
So this is where the C1 vertebrae, the very first vertebrae, would go. And then there's this hole up here at the top, and that would be where the spinal cord comes up and around down into the brain cavity itself.
So the brain cavity is locked in here to the skull. It's hard to see.
It's approximately right here.
And we think the brain cavity is probably the size of somewhere between a ping pong ball and a tennis ball.
Yes, probably closer to a ping
Probably
pong
closer
or
to a
golf
ping pong ball. So slightly smaller brain than yours,
Yep,
Andrew.
yep.
Yeah.
Fortunately.
So over here, can you show us? Okay, so that little area of where the spinal cord came through. Where is that represented here?
It's rotated, isn't it?
Yeah.
So we're looking at sort of.
That's the space
This
image.
That's true. This is actually a rendering of the air pocket that would be inside where the brain used to be.
And really, the whole brain is probably only about this size. You can see my hand there. So this is
Enlarged.
this is greatly enlarged here.
It is. That would be that's that pocket there, isn't it?
It's coming around.
It's coming around.
Oh, there
There's so
we
much
go.
data.
Right here.
So that's
where the hole is.
that hole is that whole section there, right? So give you an
Right.
idea of scale. And so really the whole thing, yeah, probably close to the size of a ping pong ball.
Right.
So
And there's
which
this
is
little
amazing.
offshoot down here. Not sure exactly what that is, but it's probably a nerve bundle area. Would come down through there and go up into the head area, probably, where the spine comes out here to the rest of the.
So it's amazing
The
to
body.
think a brain that size can control an animal so large.
So Andrew, do you know, has anyone else ever gone into the brain cavity of an allosaur like this
Not that I'm
before?
aware. This is as far as I know, this is the first time an Allosaurus skull has been CT scanned. So this will be the first opportunity anyone will have had to look inside the brain case.
So this is cutting edge research.
Exactly. It's
Really is.
world-class cutting-edge research, thanks to the people here at 3D Engineering Solutions.
So James, you're going to show me something about the teeth over here too?
So things generally fossilize and retain density values, and because of that, we can look down into the teeth and the jaw bones. This is a much better data set than what I have over in the full head. This would be off of the 16-bit data, and as you go through, you can see the teeth. All the roots come all the way down into the bottom of the jawbone. And there isn't one on this one in particular, but the teeth regrow constantly, like a shark, And I have data showing teeth pushing other teeth out of the way. Here's probably the closest to a baby tooth. Maybe here's a little part of a tooth.
That was useful to the animal because if they, when they hunted and they ripped, they lost a tooth, they'd get another one that would regrow.
Yeah. Fascinating. Now, you also went inside the T-Rex egg.
I did, and this is the T-Rex egg over here. And if I pull this out, we can look at the whole overall view. And fascinating thing about the T-Rex egg in this case, reptiles have 3 individual sacs inside of the egg. One is the embryonic sac, one's the yolk sac, and one's for gas exchange for oxygen. And there ends up being 3 bright areas in this particular egg, which could possibly be remnants of each egg sac separately. The reason it's blue, you might wonder why there's a blue egg. The colors show up a little bit better than the black and white, and if you can focus in enough, you can see little fragments in here. There's one there, there's one here, there's one over here. These are separated in one particular area of the egg. It's not, you don't find those fragments over in these other pieces. And I'm not sure what they are. They could actually be part of the bottom of the eggshell itself. The egg itself isn't very big. It's kind of flat. So it is possible that that's the bottom of the eggshell coming up through it. I have a video of a raptor egg.
Now, this is a raptor egg from our collection as well,
It is.
because we had that scanned earlier.
Yes.
And if we look at this, there's a bunch of little white spots that'll show up in this in a minute. And all these are pieces of eggshell that were inside and around this egg that showed up very, very nicely. And there's one little spot in there that was probably the most dense of anything around it. It almost didn't look like it belonged. And I could guess at what that is probably, but I don't know.
Maybe
Possibly an embryo or
possibly an
something.
embryo or the remnants of an embryo.
Remnants.
Fascinating. Well, this has really been something. This is cutting-edge research that our Director of Research, Dr. Andrew Snelling, has been involved in, and it's great that we have a company like this in the local area here, 3D Engineering Solutions, who have all this equipment, and no doubt we'll probably use them for further research in the future. Andrew and Rob, what other pieces, just for interest, what other pieces of equipment do you have here? I mean, we saw the CT scanner. There's another scanner out there.
Yeah, there's another CT scanner right beside it. It's a MCT 225. It's about half the power of the larger machine, but it's also a metrology grade CT piece of equipment. So it's unique in that way. Traditional CT technology is more for visualization, and that particular piece is more for very accurate, precise measurements and guaranteeing that.
So what other pieces of equipment do you have here? What else do you do?
Oh, we have all kinds of fun toys. It's toys for us. We're all engineers
Right,
here.
so you love using these?
Oh yeah. These are all toys. Laser scanners, structured light scanners, blue light scanners, vision systems. We have some Zeiss equipment that get us down to 1.6 microns of accuracy, which is very, very tight tolerance.
Yeah, it is.
We have long-range laser scanners, so we can scan buildings, bridges, ships. We have some medium-range things that we take all over the country. We have customers in 47 states and 7 countries at this point. All kinds of fun toys.
So Andrew is a geologist, and of course he would like to be able to go out and look at outcrops, rock outcrops, when you Andrew?
Yes, well, around here the road cuts with time degrade, and so you lose some of the details. And so I've been talking to Rob here about taking out their laser scanner, just as they used to scan a bridge downtown Cincinnati, to actually scan some of these outcrops so that we can get precise measurements, follow of individual bands and actually follow them through the length of the outcrop, relate it to the fossil content. I'm talking with a paleontologist at Bryan College in Dayton, Tennessee, who did his research work here in Cincinnati. He's interested in employing this technology, which would be sharper and better image quality than photographs for recording the details. So we're trying to push this technology to the limit to see what other applications could be used in geology and paleontology. And that's why it's so great to have a company like this here in Cincinnati that we can actually talk face to face with and go out into the field with them.
Well, that sounds like some interesting things for the future, and we wouldn't have been able to do this sort of research a number of years ago.
No.
So, I mean, when did they invent, for instance, the big machine there? When did they really come about?
CT, the CT scanning technology has been around for many years.
Right,
Obviously,
right.
medical industry was one of
Right.
the first, and so now industrial CT technology is starting to get its coming up. It's the cutting edge technology for the type of work that we do, and it is starting to proliferate and become more and more. There are still very few service providers like ourselves who offer this type of technology, but that's going to ever increase. And part of the barrier is the equipment cost. It's very expensive equipment, and it takes a lot of training and a lot of know-how and staff, and having Jim, who's got such a depth of experience, is very helpful for us.
And I imagine that sort of expertise, it's not easy to find, that
No,
sort of
it's not.
expertise. And you guys have that here. So it's not like buying a car when a new model comes out, you want to upgrade to the new model.
No, not quite like that.
But the pieces,
You do. Oh, of course, because you're the one that uses
but
it.
the engineers have already tested the pieces of the car as they go into the manufacturing phase to make sure it's going to work. So
Oh, yeah.
a lot of intelligent input goes into the cars.
That's true. That's very true.
So you said you had a picture of a bridge that you scanned in
Yeah,
Constantine.
in
Can
our
we go and have a look at that?
Absolutely.
And let's hope that this doesn't cut out. If it cuts out, we'll come back on again. So technology's pretty good when it comes to phone and video, but it's not always perfect. Think about it, it's incredible. You used to have a whole TV station and a big aerial to broadcast a signal. Now we can do it with a little iPhone, and it goes out to thousands of people, hundreds of thousands over the internet. So
So what you're seeing on the wall here is the images of the Roebling suspension bridge. This is actually laser scan data from a long-range laser scanner. The scanner's shown in this little placard over here. It's a piece of equipment from Faro. Long-range laser scanner. It's actually the most accurate long-range laser scanner that exists in the industry by almost an order of magnitude. So a very nice piece of equipment. And what you see here is about an hour and 15 minutes worth of data, taking in 6 different locations on the deck of the bridge. If you look really closely,
this is a bridge over the Ohio River.
correct, the Roebling suspension bridge.
Right,
It's actually
right near Cincinnati there.
yeah, it's the one that Roebling did before he did the one in New York, the larger bridge in New York.
Yeah, it's
Yeah.
very similar to that.
Yes,
Yeah.
very similar design. But if you look, you see little dots, and these are actually laser scan points that are captured. There are millions of these in the scene here. There's also integrated color cameras, so you get color as well. You got to watch out if it's a bright day, you'll get washed out. I can tell you where all the rivets are into this bridge within a couple of millimeters, which is fantastic.
That's amazing.
It is fantastic in a full data set. Actually, during part of the scanning, people were in the way of the scan, so there was actually ball game letting out during part of this. If you look here, each one of these little vertical stripes here is a person. This machine scans at up to 1 million points per second, so it scans incredibly fast, large amounts of data.
Is that the sort of instrument you would use if Andrew wanted to do some scanning of outcrops?
Absolutely. It would be the best one to use just because, again, it is the highest accuracy of that class of equipment that exists.
So we could get to see inside outcrops? Or?
Not inside of them, just the outside. It's all visual
Okay.
technology.
It's just
Outside.
outside.
Right.
All the
right.
details.
So what do you do for inside, Andrew?
Oh, you have to break it
Break it
open.
Yeah, but there's no scanner that can...
No, there's no scanner that can get inside.
Well, you need to invent one.
We'll look at that. We'll look at that.
Well, yeah, of course, James wants
Portable
one.
X-ray
yeah.
scanner.
So, yeah, to be able, well,
To see where the
you
fossils
couldn't
are.
X-ray when there were people there like that. But
No, that wouldn't be wise.
anyway, this has really been fascinating, and fascinating to meet the engineers here. And I hope everyone watching my Facebook here has enjoyed this. We did it in 2 parts today because it cut out for the first one, and then we reconnected using Wi-Fi. So you can go back and watch the first part if you didn't get to see that. And we'll be capturing some photos here and some video as well. And great to have you guys in the area that we can come and be able to use equipment here, like hundreds of other customers that you have. And so I'm really sure that we can be one of your customers too. So that's really great. So we look forward to working with you more in the future as Andrew does more research. And with that,
Stay tuned for some more results.
stay tuned for some more results. And with that, it gives you an idea of the sort of research that we are doing. Dr. Andrew Snelling is involved in some of the cutting-edge research here and working with one of the local universities too, Cedarville University, a Christian university. It has the only graduate
Only geology program
undergraduate
from
geology
a creationist
program,
perspective
yeah,
in the country.
creationist geology program. So headed by
John Whitmore, Dr. John Whitmore.
Dr. John Whitmore. And so they're involved with you and one of their
Yes.
students in doing the research here too. So, okay, well, with that, we'll sign off.